Hey everybody, it's Tuesday, April 6th. As you can see here in the aim today, our goal for today's video is all about how we can use simple harmonic motion concepts to solve problems. Now, at this stage of this unit, usually what I like to do is spend some time talking about how we can use all of the stuff we learned in the beginning of the unit to solve problems before we move on to the next big subtopic. And so that's what we're going to do here today. At the end of yesterday's video, we took a look at some problems that were on the first of these three worksheets that we're going to be using to sort of wrap up these concepts before we get on to the next part. And so for today's video, we're going to look at this second and third worksheet that I usually like to use when we're talking about this topic. And then we will move on to the next phase of this simple harmonic motion unit tomorrow. So if you go back to the Google Classroom page and you open up the first worksheet that is attached to today's post, you will see this problem at the very top of that worksheet. All of these problems are from the Tipper's book. This one is B7QRT05, position versus time graph of a cart attached to a spring, mass and period. And the question says a frictionless cart of mass m is attached to a spring with a spring constant k. When the cart is displaced from its rest position and released, it oscillates with a period, as they have it labeled here, tau. Usually we use uppercase T. This book likes to label it tau. Don't worry about that. It oscillates with a period given by the equation 2 pi times the square root of m over k. That, of course, is just our familiar spring period equation. It says here the graph of the position of this cart as a function of time is labeled experiment A. Graphs for two other experiments that use different masses are shown below this. The same spring is used in all three experiments. And there are a few parts to this worksheet that I'd like you to look at. We're going to start, of course, with part A. Part A says compared to experiment A, in experiment B, the cart has. And you have a bunch of different options for how the mass in experiment B might be different from the mass in experiment A. I'd like you to take a couple minutes and pause this video here and answer this question. Look at the graphs. How can you use the information from the graph to determine A, just the difference in the graphs, and then B, the potential differences in the masses that are shown here in this list? Come up with an answer, come up with an explanation, and when you hit play, we'll go over it. Now, if you look here at the graphs in experiment A and B, what you should hopefully notice is that these graphs are not situated like along the origin of the coordinate system. And so sometimes I think it's a smart idea when you're looking at these graphs just to get a lay of the land to figure out where like the equilibrium position is. And so ultimately that's going to end up being here for experiment A and then here for experiment B. And ideally, if you were going to draw this on your own piece of paper, you would use like a ruler or something. But that's where the equilibrium position is for the spring in both of these experiments. Now, the difference between these graphs that should immediately jump out to you is that the amplitude of the oscillation in experiment B is much higher than the amplitude of the oscillation in experiment A. Clearly, this object is going, as it shows here, twice as far from the equilibrium position in experiment B as it is in experiment A. What you should also notice, if you were to look at this really carefully, is these graphs totally line up in terms of the time axis that is shown here in this particular problem. The fact that they completely line up gives you a pretty big hint about what's going on here. Ultimately, the fact that these two graphs totally line up tells us these springs are oscillating with the same period. Notice if the peaks are totally lining up and the troughs are totally lining up for the entire experiment, it tells you that the period of oscillation is the same. It's really important for everybody to remember here that the period is a measurement of the time it takes for this thing to complete one full cycle. And if this starts at the equilibrium position, goes up, comes down, and then gets back to the equilibrium position, in experiment A, that happens between these 2 points that I have now shown on the screen. And for experiment B, it starts here at the equilibrium position, so we'll measure it from there. It goes up, down, and then back again right here. And notice these two dots line up. And that means the period is the same. Now, I just want to make one thing clear. You don't have to measure the period from equilibrium position to equilibrium position. You could, of course, measure it from peak to peak. And notice here, these dots are going to be exactly equally spaced as well, which lets you know that the period is the same. Or you could do it from trough to trough. which would be shown by these two dots here. And of course, it's the same for experiment B. The period is the same in both of these experiments. And the key detail here is now in recognizing how the period being the same informs you about the mass. For this one, you could say, okay, well, the period is the same. And so that might mean the mass is the same. But what about the spring constant? Is the spring constant in experiment B bigger? And is that explaining maybe some differences in the mass? Hopefully you read the initial description carefully, and let this be a good lesson to you as we now start to move very close to being in the review stage for the AP test. The initial description of this problem tells you the same spring is used in all three experiments. And what that tells you is if it's the same spring, that those springs, of course, it's the same spring. There's the same spring constant then that you're going to use in this calculation for all three experiments. And so the answer here in this particular problem, the first part, is that the masses are the same. It should make sense how the mass is going to affect the period. If an object has more mass, it has more inertia, which means it's harder to accelerate. The fact that it takes the same time to move these masses back, through this cycle tells you that the mass is the same. So what I wrote here is the answer is choice 5. Since the problem says the same spring is used in all three experiments, we know that the spring constant is the same for experiments A and B. According to the graphs, while the amplitude of the oscillations is different, the period of oscillations are the same. Since the period is only dependent on the mass and the spring constant, and the period and the spring constant are the same, then that tells you the masses are the same. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So the basic idea here in my explanation is that we base it on just looking at this equation solved for the period. It's also important to realize if you really wanted to, particularly because they're asking you about the mass, you could just do this having solved the equation for the mass, and then, of course, argued it that way. And so if you solve this for the mass, then you would get the mass is the period squared times k over 4 pi squared. And so what that would let you know is that the mass is directly proportional to the square of the period and directly proportional to the spring constant. Of course, though, the spring constant is constant. And so the basic idea is you got the same period here, you got the same mass. Let's move on to part B. Part B, the second question here, says compared to experiment A, in experiment C, the card has. So now they basically want you to do the same thing, except instead of comparing experiment A to experiment B, you are comparing it to experiment C. Take a second to pause this video here and answer this question, come up with an answer, come up with an explanation, and when you hit play, we'll go over it. All right, now clearly after looking at the first part of this question, part A, you should have a pretty good sense of how to attack this question. I think part of what you really want to make sure you're being careful about in this question comes from the fact that the equation for the period has a square root in it. And so the key detail here, I think, is in recognizing that in 1-1-1 rule problems, when you have square roots and you have obviously things being squared, you got to just make sure you're being a little careful in terms of answering the question too quickly. You want to make sure that you're really being deliberate about getting your answer. And so here, if you look, as we mentioned here for experiment A, we can measure the period from equilibrium to equilibrium. And what we should probably do here is recognize that counting the time would be a smart idea. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we'll call that 11. Looks like about 11 seconds for the period in experiment A. If you do the same thing for experiment C, then it looks like about 1, 2, 3, 4, 5, and then it's in between 5 and 6 when it gets back to the equilibrium line. So let's just call it 5.5 seconds. And so the key thing that you should be taking away from just a basic analysis of what the period actually is in both of these experiments is that the experiment C period is equal to half of the experiment A period. Notice I've written this as an equation, which is kind of hard to see there, so I'll rewrite it again. The period in experiment C is 0.5, the period in experiment A. Now, the first thing that you should be taking away from that, then, I think, is that if the period is less, think about how that's going to affect the mass. Well, if the period is less, That's because the object is easier to move around back and forth. It's getting back and forth quicker. And so the fact that it's easier to move around, well, that would be because the object has less inertia. It's easier to move. And so that means the object should be lighter here. And so it's not going to be 5, it's not going to be 1, and it's not going to be 2. We have a choice between 3 and 4. And this always comes down to that classic trick when you have something in an equation that is squared, or if there's a square root symbol, right? Like when they tell you in a gravity problem, the thing is moved twice as far away. A lot of people like to think the gravitational force is going to be cut in half. But because that distance is squared, it's actually cut by a quarter. And so here's the idea. The answer is choice 4. Of course, since the problem says the spring constant is the same because we have the same spring, we want to focus on the period. The period in experiment C is half the period in A. Since the period is directly proportional to the square root of the mass, the fact that the period in experiment C is half means the mass in experiment C must be a quarter. Of course, you could also look at this, as we were mentioning before, by just solving the equation for the mass. You get period squared times k over 4 pi squared, which shows you the mass is directly proportional to the square of the period. And of course, because 1/2, if you're thinking about this like a 1-1-1 rule question, 1/2 squared is a quarter, we get the mass is quartered. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on to part C. In part C now, it says, suppose that in a fourth experiment, experiment D, the mass used in experiment A was doubled, and the spring was replaced with the spring constant, a spring with a spring constant of 2k. The period in experiment D would be, and now they're asking you to compare the period in experiment A to this hypothetical experiment D. Take a second to pause this video here, come up with an answer, come up with an explanation. When you hit play, we'll go over it. I would imagine most of you found this one to be pretty simple. The answer here is choice 1. The explanation is pretty straightforward. It's all about the equation. This, as I view it, is about as straightforward as of a 1-1-1 rule problem you could possibly be asked in this unit. As you can see here, the period for the spring is directly proportional to the square root of m over k. And so if you thought about this like a 1-1-1 rule problem, when you were plugging in the values for your new period, you would get double the mass, double the spring constant, and of course those changes are going to cancel, which gives you that the new period is exactly the same as the old period. And so as I wrote here, choice 1, the period of the oscillation is directly proportional to the square root of the mass and inversely proportional to the square root of the spring constant. Since the mass is doubling and the spring constant is doubling, there will be no change in the period, as both of those changes will cancel each other out. That should make sense. Yes, double the spring constant means the spring is going to be exerting double the force at the amplitudes. But the fact that the mass is also doubling means that object is also now twice as hard to move. So you got double the force, double the mass, you get the same acceleration, and so it's going to take the same amount of time to go back and forth. Take a second to pause this video here and write this down. And when you hit play, we'll move on. All right, and with that brings us to the second question on this worksheet, which is on the back of that sheet of paper that you should already have open, that first attachment for today's post. And that question is B7QRT11. This question is titled Oscillating Mass on a Spring Displacement versus Time Graph, Directions. It says a card attached to a spring is displaced from equilibrium and then released. A graph of displacement as a function of time for the card is shown. There is no friction. Points are labeled A through H in the graph. The arrows and signs above the card indicate positive and negative directions for the displacement of the card. It then says for each labeled point above, identify if the vector quantity listed below is in the positive direction with a positive sign, the negative direction with a negative sign, or a 0 with just the number 0 for no direction. And then explain your reasoning. I want you to go ahead and fill out this chart, and then we will go over the answers and summarize all of the key points. Now, don't go too nuts about the explain your reasoning part. Really, this can just be facts that help you determine the sign of those quantities. But that's what I want you to do. And I know that the question doesn't necessarily call for this, but I do think it is a smart idea. You really want to make sure you're thinking about how to do this in the easiest way possible. Because I do think it is good for you to be able to do this in general, but you also definitely want to make sure that you are able to do this quick if it was something that came up on the AP test. And so being able to just recognize the patterns and go here is a very important point. So try your best to think about how you could fill this out as efficiently as possible, and then come up with reasons or the key indicators that allow you to determine the sign of each of these quantities. And when you hit play, we'll go over it. All right, so if you take a look here at this chart, what you should notice is that the easiest and most obvious thing to fill in first is the displacement. And that's because this is a graph of the displacement versus time. And so you can just read this off the graph. A is above the x-axis. It's positive. So is B. It's positive. You know what? Let's do this on the bigger one. Positive, positive. Then for C, that's at the origin, so it's 0. For D, E, and F, those are all below the x-axis, so these are all going to have negative displacements. D, E, and F, that's negative, negative, negative. And then G, of course, is back to the equilibrium position, and that's 0. And then H is positive again because it's above the x-axis. That's it. I think it's silly, in my view, to go point by point and try to fill out all 4 quantities. I think you should go column by column, because that's the way you should be thinking about this. What determines the sign of the displacement? Where the object is located relative to the origin. That's it. The points labeled show you whether it's located in the positive direction, that would be whether it's above the x-axis, or in the negative direction, whether it's below the x-axis. Now, let's move on to the column right next to it, the net force. As we said, the net force acting on this cart in simple harmonic motion is a restoring force, meaning it's always trying to move the object back to the equilibrium position. What that tells us is that the force is always opposite the direction of the displacement. If you look at the equation is Fs, the spring force, is the negative of Kx. And so the spring force is directly proportional to the negative of the position. So where we have a positive displacement, we have a negative net force. And where we have a negative displacement, we have a positive force. I realize here now that I wrote H, that should be positive. And so basically, we're just going to fill these all out as negative for the positive displacements and positive for the negative displacements. Now for the zeros, as this equation also shows, when the displacement is 0, because the force is proportional to the magnitude of the displacement, the force is 0. And that's it. Now we have our whole net force column filled out. And what you should realize is that the second we have our net force column filled out, we also have our acceleration column filled out. Because for an object oscillating on a spring, the net force is equal to the spring force. And of course, the net force is ma. That tells you the acceleration is always in the same direction as the net force. The acceleration is opposite the displacement and in the same direction as the net force. So basically, we're just going to copy this column over here. Negative, negative, 0, positive, 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 0, negative. Donezo. And now we're already 3/4 of the way done. The only thing we have to do is fill in the velocity column. In my view, this one is the toughest. And the reason why this one is the toughest, I think, is because you do actually have to go point by point. The velocity from this graph is determined by looking at the slope. Because this is a displacement versus time graph, the velocity is given by the slope. Now, of course, because the graph is curved, what you actually need to do is look at the slope of the line that is tangent to the curve. It's not difficult, but it's a little time consuming. As you can see at A, the line tangent to the curve would be horizontal. That means the velocity is going to be 0 there. Notice that that's always true at the amplitudes. So we can just go and fill in E already. E is going to be 0 as well for our velocity. So E is going to have a 0 velocity. Now for B, C, and D, the slope of the tangent line there is negative for all of them. And so you'll start to see a pattern. You got a 0, all the same sign, and then another 0. And now going to F, G, and H, if you actually just sketch in the tangent line there, you'll see that those slopes are all positive. And so the pattern here should be pretty clear. You have zeros, then same sign, 0. Of course, if there was after H a point I, we would see another 0, thus kickstarting the pattern again. And that's ultimately how it works. Notice, it also kind of works like that for net force. The zeros are just shifted, and for displacement, and for acceleration. There are patterns here, and that's an important thing to keep in mind. Take a second to pause this video and copy down this chart just in case you got answers that were different than mine. And when you hit play, we'll go over the explanation. All right, for the explanations here, I just decided to go in the order of the complexity of the quantities, and so I started here with the displacement or the position. The displacement sign is determined by the graph, right? You just read it. It's whether the point is above or below the x-axis. For the velocity, you got to look at the slope of the tangent line. The sign of the velocity is determined by the sign of the slope of the line tangent to the curve. The sign of the acceleration, as we said, is always opposite of the direction of the sign of the position or the displacement. And of course, we can say the sign of the force is always in the same direction as the acceleration, and thus is always opposite the direction of the position / displacement. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And that brings us to the last question on this sheet, which is B7 CRT06. Velocity versus time graph, frequency, and period. This is the last question on that first sheet you'll be working on for today. It says a cart attached to a spring is displaced from equilibrium and then released. There is no friction. A graph of velocity as a function of time for the cart is shown. The arrows and signs above the cart indicate the positive and negative directions for the position of the cart. And so this is the equilibrium position. It's going to move either right in the positive direction or left in the negative direction. And the first part of this question, this is another 3-part question, asks you, what is the period of motion for this cart? Take a second to pause this video here and come up with that answer, come up with that explanation. And when you hit play, we'll go over it. All right, this one is pretty straightforward, I think. Period is a measurement of the time it takes to complete one full cycle. In that amount of time, it's got to go through all of the possible positions. And so notice if we started here at 0, and I guess I can mark this in red. If we started at 0, it goes up, down, and then back again. And so that means it's completed its cycle here at 8 seconds. That tells us the period is 8 seconds. Just to clarify, because it's very easy to see on this graph, you do not need to go from equilibrium position to equilibrium position. You can go from peak to peak. Notice this peak is at 2 seconds, and this one is at 10 seconds, showing you a time interval of course, 8 seconds. And you can also go from trough to trough. This trough here is at 6 seconds. This one is at 14 seconds, also showing you a period of 8 seconds. That's how it works. It's very straightforward. Now, it should be noted as well, and I'll probably move over here now just because there's less writing, you don't just have to do this from peak to peak or trough to trough or equilibrium to equilibrium. It could be from any 2 points that are experiencing the same displacement. You could do it there at 11 seconds, and then continue that line over until it gets there the next time on the way back towards the equilibrium position. And notice that happens at 19 seconds, showing you, again, the period is 8 seconds. So what I wrote for my explanation here is 8 seconds. The period is the time needed to complete one oscillation. To determine the period, you can measure from the same point at 2 successive cycles. One after the other is what successive means. And that's it. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Moving on to part B. If you take a look at part B is asking now what is the frequency of the motion of this cart. If you were paying attention to the simple harmonic motion stuff we said before the break, this question should seem pretty easy to you. Take a second to pause this video here, try to come up with an answer, try to come up with an explanation. When you hit play, we'll go over it. The answer here is pretty straightforward, in my view. We said before the break, the period and the frequency are related by the equation T equals 1 over F. The period and the frequency are defined as being inverse quantities of one another. That's the most important thing you need to know about them. So if we look at the reference table and see the equation T equals 1 over F, that lets us know that 1 over T, 1 over the period, is equal to the frequency. So this is pretty straightforward. If the period is 8 seconds, well, then the frequency is 1 over 8 hertz. And of course, 1 over 8, 1/8 is 0.125. So the period, or excuse me, the frequency is 0.125 hertz. And the explanation here doesn't need to be that complicated. The frequency is the inverse of the period. Since the period is 8 seconds, frequency is just 1 over 8 seconds, 0.125 hertz. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And let's wrap this up here by looking at part C. I like part C. I think it is a sort of interesting, confusing, kind of weird question. It sort of helps solidify the concepts that we've been talking about since we brought up simple harmonic motion. And so I think it's a good thing for us to focus on before we move on to the next sheet. This question, B7 CRT 06 part C, says, in which direction was the cart displaced from equilibrium before it was released? There are a lot of ways you can answer this question. Give it a shot. Was the cart displaced to the left or to the right? In the positive direction or in the negative direction? Take a second to pause this video here, try to figure that out, try to figure out how you could explain it. And when you hit play, we'll go over it. All right, now there are a couple of ways that you can look at this here. And so I just want to jump right to the explanation here. The object was displaced to the left. The first way you could say it is that since the velocity is immediately increasing in the positive direction, it means the object is moving to the right. The only reason the object would be moving to the right, though, is if it was displaced to the left, since the spring is always trying to get the object back to its equilibrium position. It's an important thing to realize. It's a restoring force that causes simple harmonic motion, meaning you push the thing to the right, it's going to go to the left. You push the thing to the left, it's going to go to the right. And since we know it's going to the right, that means it was pushed to the left. Now, actually, as I was writing this answer down, it occurred to me that there's also a pretty easy way to come up with this based on what we said back in the answer to the previous video. The sign of the acceleration is always opposite of the direction of the sign of the displacement. And since they're giving you here a velocity versus time graph, you can use the slope of the tangent line to figure out the acceleration. The slope of the tangent line for this graph starts out as positive. That means the acceleration is initially positive. And if the acceleration is initially positive, that means the position is initially negative. So I wrote here, also the acceleration is always opposite of the position. The slope of the tangent line for the velocity versus time graph gives the sign of the acceleration. So the fact that the acceleration starts positive means the object's position is initially negative. Now, I don't think you have to write down both of these, but I would write down at least one of them depending on which one speaks to you more and which one you think will be an easier way for you to answer a question like this in the future. Take a second to pause this video here and write that down. And when you hit play, we'll move on to the next sheet. All right, moving on to the next sheet here, as you can see, we have the question B7RT01. These first two on this sheet, I think, are very straightforward. So let's just jump right into them. B7RT01 says you got a mass on a horizontal spring. They're asking you about the oscillation frequency. A block rests on a frictionless surface and it's attached to the end of a spring. The other end of the spring is attached to a wall. 4 block spring systems are considered. The springs are stretched to the right by the distances shown in the figures and then released from rest. The blocks oscillate back and forth. The mass and force constant, that really means spring constant, of the spring are given for each case. And the question says to rank the frequency of the oscillatory motion of the block. Can you just calculate the frequency for all 4 cases and compare? Of course. Don't do that. That's insane. There are much easier ways to answer this question. And that's what I want you to think about here as you're going through and answering. So take a second to pause this video here, come up with an answer, come up with an explanation, and when you hit play, we'll go over it. So the key to answering this question, in my opinion, is the equation for the frequency of the spring. 1 over 2 pi times the square root of k over m. Now, obviously, you could just plug in k and m for all 4 cases and calculate the frequency. But what you should recognize is the frequency is proportional to the square root of k over m. Taking a square root 4 times is annoying, though. So what you should realize is that if the square root of that ratio is going to be bigger, well then the ratio is going to be bigger. That's always true. So we can say the square root of k over m is proportional to the ratio k over m. And that's what you should really be looking at for these problems. So if you look at A, you got a 5-to-1 ratio of spring constant to mass. For B, 5-to-2. For C, 4/5, 4-to-5. And for D, 1-to-1. And whichever ones have a bigger ratio of k to m, you're going to have a bigger square root of k to m, which means you're going to have a bigger frequency. So the biggest one is A, 5 over 1 is 5. 5 over 2 is 2.5. So then we have B. Then we have D, 1 over 1 is 1. And then, of course, the only one that's less than 1, 4 over 5, or 0.8, is C, and that is our ranking: A, then B, then D, then C. And the explanation is going to look a heck of a lot like what I just said. The frequency of the oscillation is directly proportional to the square root of the spring constant and inversely proportional to the square root of the mass. This means, in an indirect way, we can say that the frequency of the oscillation is proportional to the ratio of the spring constant to the mass. The ratio is all that matters. This means for the system with the largest spring constant to mass ratio, the frequency of the oscillation is larger. That point here, starting there and going through to the next two lines, is very important. It's all about the ratio. Now, the last line is not like overly important, but I do think it should be mentioned that the amplitude has no effect, only because they're trying to trick you by showing you different amplitudes here. Is the amplitude in the frequency equation? No. That means it doesn't matter. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to B7RT04. That is the next question on this sheet. Mass on horizontal spring systems 2, period of the oscillating mass. I'm not going to read the beginning part because it's the same thing as the last one. It says here, rank the period, the time it takes for the block to complete one cycle of the oscillatory motion of the block. And honestly, the fact that they told you that is generous. It's a gift. Now, the thing that I would caution is that despite the fact that the setup here is similar, it is not the same, meaning the numbers are different. You could tell that if you just look at the cases individually. So be careful with these. Take a second to pause this video, come up with the ranking, come up with an explanation, and when you hit play, we'll go over it. Okay, so looking here, despite the fact that these are not identical scenarios, the approach we're going to take is going to be remarkably similar. You look at the equation for the period of a spring, you get 2 pi m over k, or 2 pi times the square root of m over k. And so just like we said before, the period of the spring is directly proportional to root m over k. We can also then say the square root of m over k is going to be bigger if the ratio of m over k is bigger. And so what we're looking for is the ratio of the mass to the spring constant. Here, we have 1 over 5 for A. For B, we have 2 over 5. For C, we have 1 over 1. And for D, we have 4 over 4, which is 1 over 1. And if the ratio is bigger, that means the period is going to be bigger. Notice the biggest ratio then is C and D. C is equal to D, starts us out. Then we go biggest to smallest. So that would be B and then A. So we have C equals D, then B, then A. And the explanation we can write for this one is going to look almost identical to the one we had for the last one. The period of the oscillation is directly proportional to the square root of the mass and inversely proportional to the square root of the spring constant. This means, in an indirect way, we can say that the period of the oscillation is proportional. Notice I didn't say directly proportional, but it's proportional to the ratio of the mass to the spring constant. This means for the system with the largest mass to spring constant ratio, the frequency of the oscillation is larger. And of course, then we want to throw in that last part about how the amplitude of the oscillation does not matter. It's very important to mention for questions like these, it would have taken you so long to answer these if you actually calculated the frequency 4 times and then calculated the period 4 times, when all you have to do is compare how the mass and the spring constant are, and then you've got your answer. Take a second to pause this video here and write that down. When you hit play, we'll move on. All right, moving on to the back of this sheet now, we are in the home stretch. We are up to the second to last question we were going to answer for today. That is B7SCT10, oscillating cart, period. This question says a frictionless cart of mass m is attached to a spring with a spring constant k. When the cart is displaced 6 centimeters from its rest position and released, it oscillates with a period of 2 seconds. 4 students are discussing what would happen to the period of oscillation if the original cart with a mass m was displaced 12 centimeters from its rest position instead of 6 centimeters and again released. And then we have 4 kids' options. Now, the first question we want to ask here is, what's actually changing in this problem? If the cart was originally pulled 6 centimeters from its rest position and then released, and now it's being pulled 12 centimeters from its rest position and then released, what is changing? And the thing that's changing here is the amplitude. That's an important thing to realize. And so now, if you recognize that the only thing that's changing is the amplitude, then you can evaluate these kids' claims. Aiden says since the spring is stretched more, the force will be greater, causing a greater acceleration and greater speeds overall. Since the cart is moving faster, the time will go down, probably to 1 second since the force is doubled. That's pretty reasonable. It makes logical sense. Barb says the cart has farther to go now, and so it's going to take longer to make a complete cycle. It's going to go farther on both sides of the rest position, so the round trip is 48 centimeters instead of 24 centimeters. Period is going to double. Also reasonable. Charles says the cart has 4 times as much energy, and the conjugate variable for energy is time, according to Heisenberg's uncertainty principle. Now, the conjugate variable for energy is time, according to Heisenberg's uncertainty principle. What I hope everybody realizes is you should not read any more of this, because Charles is out to lunch. Because Heisenberg's uncertainty principle is a principle of quantum mechanics, which only has to do with atoms. And this has nothing to do with that. So Charles is out. Forget him. Dallas says stretching the spring twice as far means the K is twice as big. And since the period is 2 pi times the square root of the spring constant divided by the mass, doubling the spring constant and leaving the mass alone is going to double what's inside the square root. After we take the square root, we get a period of 2 seconds times the square root of 2, or 0.414 seconds. Take a second to pause this video here and evaluate these claims. Try to come up with an answer. Who do you agree with? Who makes the most sense? What do you think? And when you come up with your answer and you come up with your explanation, hit play, and we'll go over it. Okay, so going through these claims here, as we said, Charles is wrong. And if you were listening carefully to when I read Dallas's claim, the first thing that he says is the spring constant changes when the spring is stretched more. And of course, the spring constant is correctly named because it is constant, and so it's not going to change. And also, they say you're going to double what's inside the square root, and so you're going to have 2 seconds for the period times the square root of 2, and the square root of 2 is 1.414. And so 2 times 1.414 is going to be like 2.8 something. And so not only is the concept wrong, because the spring constant is, you guessed it, constant, but the math is also terrible. And so now we have a choice between Aiden and Barb. And what Aiden says on some level makes sense. And what Barb says on some level makes sense. And the correct answer is a combination of what both of them say. And so you can agree with none of them if you are to get the correct answer here. Aiden talks about how the spring is going to be stretched more, so there's going to be more force. That is a fact. It is going to make the thing accelerate more, and it's going to make it go faster. That is a fact. Barb says the cart has farther to go now, and so it's got to travel a longer distance. That is also a fact. They fail to account for what the other is saying. Aiden is right. It's going to go with more force, more acceleration, more speed, but it also has to go farther, like Barb says. And so the fact is, when you combine both of those points of logic, it tells you that the amplitude is not going to affect the period. That's the key detail here. None of them are correct. The period of the oscillation is not dependent on the amplitude of the oscillation in any way. The equation for the period of the spring is 2 pi times the square root of m over k. And it says that the period of the oscillation is directly proportional to the square root of the mass and inversely proportional to the square root of the spring constant, but is not dependent on the amplitude, which is why it isn't in the equation. This makes sense because even though the cart has to travel a larger distance, the spring is also exerting a larger force because the spring is stretched more, and so the period remains the same. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. When you hit play, we'll move on to the last question for today. Last question of the day here, B7SCT07, mass on a vertical spring acceleration. A mass is oscillating up and down at the end of a spring. 3 students are discussing the acceleration of the mass. Aileen says, I think the acceleration of the mass will be largest when it is at the end of its oscillations turning around. That's where the spring is stretched the most. Bridget says, I don't see how that could be. Its velocity is 0 at that point, so its acceleration has to be 0 also. Chandra says, I disagree. The acceleration will be largest when the mass is halfway between the middle and the end, because that's where its speed is changing the most. The question says, with which of any of these students do you agree? And to explain your reasoning. Take a second to pause this video here and come up with an answer, come up with an explanation. When you hit play, we'll go over it. The correct answer here is given by Aileen. The key detail here is all in the equations. The spring force is directly proportional to the magnitude of the displacement. And so when the spring is stretched the most force is exerted by the spring, and that's why it's accelerating the most. You should definitely recognize that just because the velocity is zero does not mean the acceleration has to be zero. If you're forgetting that, think about the projectiles when they get to their max height, or just an object thrown straight up in the air. Yeah, when it gets to its maximum height, its velocity is zero, but it's accelerating due to gravity the whole time. The answer here is Aileen. Since we know the force is largest when the distance from the equilibrium position is largest, and the acceleration is directly proportional to the net force, the acceleration is largest when the spring is stretched the most. Take a second to pause this video here and write that down. And when you hit play, we'll move on. And that is it for the problem-solving portion for today. Really, the only other thing I want to do, and this is not going to take very long, is I want you to write down one important note. Because in all of the problems we looked at today, until that very last one, we were dealing with objects that were oscillating on horizontal springs. And in the last one, the object was oscillating on a vertical spring. And what usually confuses people about the vertical spring system is that you have the spring force acting and gravity acting. And that usually confuses people because the fact that both of them are acting at the same time, you might think will change the situation. What I am telling you is that it does not. The net force is still maximum when the object is at its amplitudes. It is still zero at the equilibrium position. The velocity trends are the same as when the spring is horizontal, and it's the same thing for the acceleration. The key note here is, for a vertically hanging spring, the force of gravity has no effect on the oscillation period or frequency, and only the location of the equilibrium position. This makes sense because even though the force of gravity speeds the object spring system up on the way down, it actually slows it down on the way up. And so the period and the frequency remain the same. That's the key detail. It may confuse you thinking, well, gravity is going to be acting the opposite direction of its velocity on the way up, so it's going to be slowing down. In a lot of cases, the spring force was always doing the same thing anyway. The spring force is a restoring force. It opposes the motion a lot of times. It aids the motion other times. The key detail is that the only thing that changes for a vertically hanging spring is that the equilibrium position changes. And so I'll actually draw that in a picture. For a horizontal spring, the equilibrium position is going to be wherever the spring force equals zero. For a vertically hanging spring, and you should probably already have a sense of this already, for a vertically hanging spring, the equilibrium position is not going to be where the spring force is zero. It's just going to be where the spring force is equal to the force of gravity. And that's it. And with that, that's it for today. Tomorrow, we are going to move into the next phase of this unit, which is to talk about, now that we finished the forces analysis for these objects and these systems, we're going to take a look at how an energy analysis can be used to describe the motion of a simple harmonic oscillator. All right, everybody. Have a good one.